By Jacopo Viti at the Dresden Institute, Max-Planck.
Yes, so first of all, thanks to the organizer for this nice possibility to present my recent work. So the title of my talk is this one. So I will speak about inhomogeneous quenches. I will tell you what they are, and I think we have already seen a lot of light cones in this conference, but I will show you one more, and then I will try to convince you, actually try to prove that somehow inhomogeneous quenches, they are related to phenomena in statistical mechanics, which is called the phenomena of Arctic curves. Okay, I will tell you what they are. Okay, so let me thanks also all my collaborators during the last years, from whom I learn a lot about non-equilibrium quantum dynamics, transport. So some of them are here. So this is Alberto Biella, Denis Bernard, Davide Rossini, Andrea De Luca, Benjamin Doyon, Rosario Fazio, Jérôme Dubail, Leonardo Mazza, Masoud Ake, Jean-Marie Stéphane, Nicolas Legras. I didn't find a bigger picture, and Gabriele Martelloni. Okay, so what is the problem that I want to discuss? So I want to consider non-equilibrium quantum dynamics in one dimension, but starting from a state which is inhomogeneous. So my initial state will have a non-trivial density profile. For example, there will be more particle on the left than what I have on the right, or that it might have some non-trivial energy profile. For example, you can think to prepare your system in as a tensor product of two Gibbs density matrices. So on the left you have a certain temperature, and on the right you have another one. But what is also important is that the system locally looks like an eigenstate of the Hamiltonian, which drives the final time evolution, but is not the ground state. By no means is the ground state. Is a very excited state, for example. Okay, or a mixed state. So if this is the case, and for example the final Hamiltonian is just differs from the initial Hamiltonian by some change in a boundary condition. So for example, you can think to connect two initially disconnected chain by just adding one link in the middle. Then the dynamics will be non-trivial for short time. This is a space-time diagram near the center of the chain. Okay, so something will happen to the state near the center. Then of course excitation will spread ballistically in the system, and they will develop a light cone, and if you take a slice at fixed time of, for example, a density profile or an energy profile, what you will expect is that outside this light cone the degrees of freedom of the system will be frozen. Let's say they will be stuck to the value that they have initially, because the system doesn't know that the propagation, that the disturbance has arrived here. Inside the light cone you will have some smooth interpolating function for the density, for example, and again outside the light cone the degrees of freedom, there will be still frozen, and for example correlation they will be the same as you have at time equals 0 in your initial state on the right. Okay, so this is my general framework, and this is a plot which I take from this nice and recent paper by Romain Vasser, Carrache, and Joël Moore, in which they studied, for example, the XXZ spin chain at different temperatures, and they so this is just for the plot. So this is on the MRG simulation in which you see that there is an energy current in the system which spread. So there is an inhomogeneous region basically which this energy current is different from zero, and this inhomogeneous region spread ballistically. So at fixed time you slice and you ask the question, what will be this, for example, density, this energy current profile. Okay, so this is the type of question that that I'm interested in today.
But you're
Yeah.
starting from a pure state, right?
Here not.
No, you are.
Both. Let's say both. I will do either. I will speak either about this problem, in which you don't start from a pure state, or let's say a case in which I start from a pure state. For example, it can be a ground state of a certain fermionic chain, but with a KF which is not pi over 2. So it's a pure state in that case. Both the cases, they can be treated, and they are interesting. Yes. Okay. So right. So let me speak first. I will come.
I think you are saying that even in the case of two temperature, you will have the Arctic Circle rule? Or
No.
Okay, that I think was the confusion.
No. It is interesting to see what will be, but it will not be an Arctic Circle in that case. Yes. Okay, good. So the connection with statistical mechanics concern the pure state case. This is somehow another case in which you can study in real time quantum quenches from an inhomogeneous initial state. Okay, so let me speak about energy, first about energy transport, and then I will go back to particle and the articles. Okay, so, right, so the first question that concerns, for example, because also energy transport is quite peculiar in 1D, and I will show you why it's actually interesting. So the first question that you might ask about energy transport is what will be the current? So how can I compute the current? And well, it's of course a not easy question, and there is actually a nice result which was proposed by Denis and Benjamin, which I found particularly interesting because somehow it is telling you that there is a sort of universality in energy transport in 1D as far as you take a gapless Hamiltonian and you look at the system at low enough energy. But I have to say, if you look at this picture here, that of course, I mean, this energy profile, this density profile doesn't look homogeneous. So strictly speaking, the formula here is a prediction for a fixed x and very, very large time. Okay, so basically deep inside the light cone. Okay, so why I'm presenting you this? Because I told you that I find interesting, because basically for two reasons this is interesting. The first reason is that this formula holds in general, I mean, as far as you consider a gapless quantum system, and it's telling you that there will be always, at low enough temperature, a ballistic component for energy transport. But this is actually quite remarkable, if you think. And you see that this universality shows because of the appearance of the central charge of the CFT. So let me show you a numerical check of this universality to convince you that it is actually true. And so the example which I want to present you is taken by this paper here that we did some 1 year ago with Andrea and other people. So this is a numerical simulation of the energy for which is the MRG simulation in which the system which you consider are two XXZ spin chain with different temperature, and you couple them together, and you wait some time to get certain stationary energy current. And the different curves, they are plotted for different values of delta, which is the anisotropy. So you see quite nicely actually that these curves, which are plotted for different deltas in the XXZ, they merge at low enough temperature, and they agree with this formula. So this is a nice proof actually of this universality, which I was which is predicted by this formula here. Of course, you have another interesting question is how can I describe the curve for all the values of the temperature? If I increase temperature, then the system will actually knows about its microscopic details, and because more and more states will be excited, and of course you lose universality, right? So the way in which we compute these continuous curves, which they fit quite well with the DMRG, was using Bethe ansatz. But if you want to have more details, you can ask Andrea, for example.
May I have a curiosity?
Yes.
The small difference that you see there, you think it's DMRG that's not good enough, or it's...
Well, I think DMRG we have to trust. The small difference might be related to the way in which we construct this NES, probably, which was using standard conserved charges of the transfer matrix. We didn't include the new quasi-local, but this we might discuss later. Actually, I don't have a clear answer why this was not exact.
Jacopo,
Yes.
The life temperature is fixed to some value, right?
Yeah, right, yes.
Some high temperature, or
I think you see from here when it is 0, the current was probably fixed to, I don't know.
okay.
Well, from 2 and 4, I don't know. Yes. Okay. Okay, good. So, so this was a question about universality and the energy current for a pure integrable model, which was XXZ, in which we know that the current is special because it's a conserved quantity. So it commutes with the Hamiltonian. So you might ask, well, maybe I see this persistent energy current because the current is conserved, because there are some effects of integrability. And this is, of course, an important, interesting question to investigate, and that's basically the content of this new work on which we are still working. But I want to present some simple preliminary results. So here we start with two XXZ chains, which initially, again, they have different temperatures, but they also have different anisotropy parameters on the left and on the right. Okay, so in this case here, of course, the model is not integrable and the current is not conserved. So the current now, but you can always write an energy current, just commuting with the Hamiltonian, the local density, is not conserved. But nevertheless, at low enough energy, the system you can be treated with field theory again, by generalizing some techniques that Denis and Benjamin developed, and because the theory which described the low energy part of we described the system, and the low energy is are two Lattinger liquid now, which have different Lattinger parameters. So in the language of CFT, they are different. They are boson with different compactification radius. But you know that this theory can be treated again, and you can also write an energy current in this case at low enough energy. And this is how it looks like. So it's very similar to the other formula. C is 1 in this case, but you have a prefactor which contains some, let's say, transmission coefficient, which depends on the two compactification radius of the boson. Okay, so why this is interesting? Because again, even if the model is not integrable and the current is not strictly conserved, it's telling you that at low enough energy there is again a ballistic component for energy transport. So that's
What is little r?
the compactification radius of the, I guess is 1 over 4 pi square root of k Lappinger in the usual notation. And it is related to delta, because k is related to delta. Okay, so here you see a numerical check for this formula, which again we did thanks to the effort of the people here that are very good in doing the MRG. And so this is a plot of the energy current as a function of time. And you see that again you find a plateau. This plateau is robust. So the simulation were not able to run as long as to somehow see this current flowing to 0, which what you would expect a priori, because the model is not integrable. And this is a check of the prefactor. So we have the current at some temperature, which is plotted as a function of t square, for example, t square left, and you see that there is a straight line, and the coefficient agree with what is written here. So that's what the interesting point of this is. As I repeat, the fact that you don't have an energy conservation law, current conservation law, but still at low energy the system has a persistent energy current, and you have to understand why this happens and what will actually also happen for large enough time, for large temperature also. But this I will not address now. Okay, so far was for the energy current. Now I'm switching the topic a bit, and I want to speak about particle transport and density profiles. Okay, so now my initial state will be a pure state, and I will try to understand particle transport. Okay, so then let's say a very nice setting to study this problems is the following. So it's very simple but non-trivial. You will see that there is some nice there are some nice observation in this problem. So I start from two. Let's say, so I'm considering two fermionic chain now. So someone like to call XX chain or a simple tight binding model, okay, which the Hamiltonian is just a pure open term. And I prepare my initial state in this way here. So on the left, I have a Fermi C with a certain value of the Fermi momentum, Kf, which is larger than pi over 2. So that means that I feel the single particle energy levels up to a certain value which is larger than pi over 2. And on the right, I do the same, but now the Fermi momentum is less than pi over 2. Okay, so this is my initial state. If you want, you can also say that you have a Fermi momentum which depends on position. And then at certain time t equals 0, I couple the system. And what you will see clearly is that the particle on the left, they want to go on the right, and they will produce a particle current. So in particular, this particle current will be different from 0 for small time only near the junction, because again, here the system does not know anything about the the fact that I added a link. And then as time increase, I will develop a light cone, because this particle, they will travel ballistically and spread inside the bulk. Okay? Okay, good. So this is again my Hamiltonian, I repeat, and as I told you, there will be a beautiful light cone which appears. So this problem, of course, is not new. It's one of the simplest problems you can think about when you think about transport, and it was studied by many persons, and all say something interesting about it. I will try to give a new perspective on this problem, which is somehow unifying all of this point of view. Okay, so right, so suppose that I want to study the green function of the fermion, so at equal time. So I destroy a fermion in position y, and then I create a fermion back at position x. So this is the basic object correlation function that I want to study now. So because of Fourier transform, because of translation invariant, you can rewrite this correlation function as a double integral. This is the Brillouin zone from -pi to pi, and you will have factor exponential of the dispersion relation, because this just comes from the time evolution, and then the factor kx and qy, which comes from Fourier transform, and then a form factor f, which is the expectation value in the initial state that I took, which I repeat are these two Fermi seas of the final of the fermions. So this is quite I mean, this is of course very simple. This function is not completely obvious, but you can compute. So now imagine that you want to take the large x and t limit here to see what will this correlation function will look like for large x and large t. So what you have to do is, well, stationary phase approximation, right? So you take this phase and you take the derivative with respect to k and q. Of course, the equation they decouple. Okay, so for example, if I take the derivative with respect to k, I get x minus t, the group velocity as a function of k, right? So the stationary points, actually, on which I have to expand this double integral, they satisfy the equation that the velocity of the particle at the stationary point is x over t. And this actually explains immediately why in this large x and t limit, all the function, all the correlation function, the density profile, etc., they will be just function of x over t. So this scaling behavior just follow from a simple stationary phase argument. Okay? And of course, it's true for any fermionic problem, independent, which is not dependent from the particular dispersion relation that you took. Okay, so now let me analyze the stationary phase equation and use it to compute the correlation function as a function of x. So I will get this.
Sorry, Jacopo,
yes.
you are telling that no one realized before.
No. Because no, there is a reason why people, maybe they were not that interested, but another reason is that somehow this type of quench, what people did was to, so Bettelheim, Glatzman, they did in the continuum, so it's not really the lattice model. But even they didn't do stationary phase. And the paper of Antal, etc., Gunther Schutz, so what they did is to express the time evolution of the fermions in terms of Bessel function. And then you expand the Bessel function, but this somehow hides the fact that behind all of this there is a general, simple general stationary phase analysis. Yes. Right. So No, actually, people they normally fit. If you see this paper by Antal, etc., they always saying that there is this emergent scaling limit in which all the function they
I
look.
remember that.
But there is no reason why, and the reason is actually this simple observation here. Okay, so right. So let me now explain you how you use the stationary phase equation and the solution of the stationary phase equation to get explicit expression for the correlation function in the scaling, so-called scaling limit. So x and t both very large. Okay, so the stationary phase equation, if you fix time, so I'm taking really this slice now in the space-time diagram. So if you fix time, the stationary phase equation is a curve in the plane kx, and the curve is just x over t equal v of k, which in my case is sine k, right? So this is the curve in the kx plane, okay, with a fixed value of time. And then the statement is that the stationary points, they have to lie on this curve. So when you're supposed to fix x, now the position in which you want to look your correlation function, so if you fix x, you have to take into account the points which lies on the line for a fixed value of x. So you see immediately that if x over t is larger than 1, there are no points on the line. And this means that the correlation function, they decrease exponentially to their value. You also say that the stationary points, they are purely imaginary, but that's the same. So they decay immediately to their value, which is fixed in the initial state. And that's what you actually see here. Right. So actually, mathematically speaking, this is telling you that the derivative of the correlation function is 0. But that means that by continuity, it will be the one that you get for, let's say, x going to plus infinity, which is the one that you get in the ground state on the right. So then there is a second region between x over t equal 1 and here, x over t equal, I guess, sine of kf left, in which you took two stationary points. And this, when you express, when you do the usual stationary phase analysis, you expand up to second order, turns out to give you the front. So the fact that actually here the correlation function, they are inhomogeneous. So this is the light cone. You are at the front of the light cone. Then you move again, you slice here, and you see that there is only one stationary point. But there are actually two, one for each clouds of fermion, but they coincide. And it turns out again that if you take the derivative of the correlation function respect to t or x, is still 0, because these stationary points basically they cancel, and that's why you get in the center again a translation invariant non-equilibrium stationary state that you call NES. And on the left side of let's say of the x line, of course, I mean the curve is symmetric. Okay, so this is just so this is why the stationary phase analysis provides you immediately this nice way of deriving the inhomogeneous density profile. Okay, so notice here that there is something peculiar which happens at the edges of the front, because if you see at the edges of the front, the two stationary points, they collide. And this is this is a special point, because when two stationary points collide, something has to be changed in the stationary phase analysis. That's what I want to discuss now, because when you are at the front, when x over t is going to 1, then these two stationary points here, they collide. Actually, this point is k equal to pi half in this case here. But that means that the second derivative of the phase is 0, right? So you have to expand up to third order now to get the behavior of the correlation function at the tip of the front. And you know that when you expand up to third order a Fourier transform, what you get is an Airy function, right? That's usual in the stationary phase analysis. Okay, so the statement is that if you expand up to third order the correlation function near the tip of the front, what you get is, of course, is not really an Airy function, but is something very close to an Airy function, which is called the Airy kernel. And this Airy kernel is a product, basically, of Airy function, in a way, divided by x minus y. Okay, to get this Airy function, to get the Airy kernel, you also have to rescale appropriately the position x. So you introduce this scaling variable, and then it's very easy, actually. It's amazing how it's easy to get this Airy kernel from the stationary phase analysis. But if you go a little bit more in deep, then you might ask the question, well, you might ask question, for example, about the full counting statistics of the particles at the tip of the front. And the full counting statistics is related to a Fredholm determinant of the Airy kernel, which is the Tracy-Widom, which and from that you can also show that the probability that the rightmost particle is at position x is, let's say, is between x and x plus dx is Tracy-Widom distribution. So it's just basically related to the coalescence of the stationary points near the tip of the dispersion.
So shouldn't you get an infinite number of oscillations, not just the two oscillations you showed? If it's an area function, it will have an infinite number of...
Yes, but you see them actually here.
Oh, okay.
You see that there are many.
Oh, there they are. Okay.
Yeah.
All right.
Yeah. Yes. Right. Okay. So basically, this Airy kernel behavior is somehow typical of the fact that you pass from inside the light cone to outside the light cone in a way, like the Airy function does for all this type of problem in quantum mechanics. Okay. So now let me study another quantity which also John mentioned before in his talk. So this quantity is the Loschmidt-Echo.
Sorry, Jacopo,
Yeah.
before you change subject, go back to one slide.
Yeah. Here.
How all this is related to the solution of the effective initial condition?
Is closely, very closely related. Yes, it's very, very closely related. It's a real-time version of. It's very closely related. Yes.
We start from a different.
No, the
There
result
are-
is the same.
Yeah. But this we discovered later. Actually, Spoon make this remark. Yes, but they are actually the same problem, but somehow looked from different angles. Yes.
90 degree I and
Yeah. This will come actually in a moment.
Pre-computation.
But this will come in a moment, actually. Yes. Okay. So. Right. So now let me go to this other topic, a big topic. This other question. So the question is about the Loschmidt-Echo now. So I'm starting with my again free fermion problem, and I put all of my fermions on the left. Okay. So this is so here we have one fermion, and 0 fermion on the right. So basically, this is an extreme case of the quench which I showed you before. So essentially, kf left is pi and kf right is 0 if you want. Right. So I will show you why I'm doing this. Okay. So now let us think what the Hamiltonian does on the initial state, which is the domain wall initial state. Okay. So if probably this is related also to what you wanted to, yeah? Right, yes. But there is a lot of mapping here between different models, yeah. Okay, so the Hamiltonian, when I apply to this initial state, just move this particle to the right. It cannot do nothing else. cannot do nothing else, okay? So let us apply the Hamiltonian twice. So what you can do is that you can move this particle further to the right, you can move this particle to the right, or you can go back to the initial state. Okay, so that means that basically if I apply twice the Hamiltonian, I have a chance to go back to the initial state. Okay, so now let me ask the question of what is the generating function for all these paths which start from the initial state. They apply, let's say, n times the Hamiltonian, and I go back to the initial state, right? So this you might call returning probability, Loschmidt-Echo, etc. But in this combinatorial context, somehow is this generating function. And what you discover, if you really count the number of paths, which is non-trivial, but you can do, because it's a quite complicated combinatorial problem, you can actually show that this Loschmidt-Echo is a Gaussian, but it's a Gaussian at all times now. It's not a Gaussian only for small time. That's the nice properties now. That this function is a Gaussian for any values of time. Okay, and I will come back to this actually. Okay, so now let me just briefly somehow put a bit of suspense, and because before going back to this Loschmidt-Echo, and just telling you what is this Artig-Silkor theorem. Just keep in mind what will be what I have in mind now. So this is a problem in combinatorics again. Basically, it was it emerges in mathematics in the study of domino tilings, or if you want dimer covering on so-called Aztec diamond. So this is the lattice, so this is the Aztec diamond. For some reason, mathematicians, they like to have this name. So this is the Aztec diamond, and you will see there is an Arctic circle. Okay. So, but anyway, so this is the Aztec diamond. Is this object here? And you ask the question, in how many ways I can cover the Aztec diamond with dimers? So the remarkable fact is that, so you have to count the number of configurations, basically. This was the original problem. Okay, but the remarkable fact here is that basically the orientation of the dimers, if you draw a random configuration which respects the dimer rules, so the orientation of the dimer in such configuration is frozen at the corner. So basically here you will find always horizontal dimer, also here, and here you will find always vertical dimers. No way. Try to do it. Take some Aztec diamond which is small, and you will see that this dimer will turn out to be horizontal here, and vertical there. This is a remarkable fact actually. And the point here is that the orientation of this dimer can fluctuate only inside a central region. That mathematicians show that for large, let's say, lattice is a circle. So that's the statement of the article.
Is your statement probabilistic or?
It's probabilistic with probability 1.
Okay.
In the limit, right?
In the thermodynamic.
In the limit.
1 minus epsilon, I don't know, but somehow it's a very precise statement that you can say with probability 1. This is, if you find a configuration which does not respect that, you can show to some mathematician, because I think it's quite unlucky.
Will make
Yes. Okay. Of course, there is one, but it is actually easy to find. But this is right. Okay. So now let me go back to the Loschmidt-Echo. So now let me do the following. So let me do this. So what basically John and Pasquale, they taught us many years ago. So just replace time with imaginary time. So I substitute t with minus 2 IR, in my formula for the Loschmidt echo. And of course, I mean, this is a very trivial manipulation. The Loschmidt echo in imaginary time is still a Gaussian. It's still a Gaussian of R square now, okay? But the point of this simple observation is that now you can interpret this Loschmidt echo as a free energy, because you are in imaginary time on a slab, and the slab has length 2r and is infinite in this direction, okay? So actually, the fact that the free energy is not diverging linearly with L now is non-trivial, right? Because this is not what normally you would have in statistical mechanics. Of course, it has to do with the boundary conditions that we have that are really special, because this is a domain wall initial state, right? But somehow what this formula is telling you is that the free energy can fluctuate only inside an area, which has dimension r squared, and nothing happens outside, right? So this is somehow the crucial observation. And now suppose that I want to compute a density profile on the slab for fermions. So this function rho of x, y, and r now. So y is this direction here, x is this, and 2r is the length. Okay, so if I want to compute the density, then I have to start with my initial state, which is this domain wall initial state. Then I have to evolve in imaginary time up to a value which is r plus y, okay? Then I measure the density of the fermions, and then I evolve back up to the top of the strip here. And then I impose again my domain wall boundary condition. Okay, so this is a free fermion problem with the same Hamiltonian, so the opening Hamiltonian, but in imaginary time. Okay, so let's see what the density profile will be. So this is the initial state, the final state, and then we run, let's say, actually you can numerically even compute this density profile, and it will look like this. Okay, so basically you see that the density profile in imaginary time is fluctuating only inside a circle. And outside is frozen. You can actually, as I told you, you can do exactly the same stationary phase analysis that I did for the real-time problem. There are slightly differences, but I will tell you in the next slide. And to compute the density for x and y very large in the thermodynamic limit. Okay, so the density is this one for the imaginary time problem. And you see that the limiting shape is a circle, because it's the point in which the argument of this arc cosine is 1. So it's a circle. Now, suppose I'm doing the analytic continuation as, again, the real quench problem was suggested by Pasquale and John. So you have to take t equal iy and set the length of the slab to 0. Right? Now, if you do that, you are going back to the real-time quantum mechanics problem, and what you see is a light cone, right? Because if I do that, I get exactly x over t, and it's nice that there is a minus y square here, actually. Okay, so that's about the key observation, the key computation, right? So if you take the quench from the domain wall initial state in imaginary time, so this light cone becomes a circle. And
Of course, that's really not allowed what you just did, you know.
Here, taking this,
Because this is an asymptotic behavior in a limit, and you've analytically continued an asymptotic behavior. And
You-
the asymptotic
yeah.
of the analytic continuation is
I-
not the analytic
yes,
continuation of the asymptotic.
yes. So this, of course, is cheating at this level here. I totally agree, but you can actually do the computation more carefully, computing the real correlation function in imaginary time, show under which condition you can continue them in real time, and take the analytic continuation, let's say, not in the asymptotic regime, and show that you get exactly the same correlation function for the real-time problem. So actually, it is a property that you can show independently on how x, y they are large. If x and y they are large, it's exact for any x and y under a certain assumption that are written in the paper. Okay, but I agree. At this level is a game. I'm playing a game to somehow convince you that the two things are related. But the more serious computation you have to do with the exact formula for the correlation function. Right. Okay. So let me show you how you compute essentially this correlation function. So you start with this again, C dagger x y c x prime y prime. So the problem of imaginary time is the following. So the problem of quantum mechanics is imaginary time is this one basically, that here and so on the left and on the right you have the same operator, and that's why it's non-trivial to use Baker-Campbell-Hausdorff formula, because normally what you will do is to commute this with this, this with this, and kill this one. But this now you cannot do. So that's why the problem of doing quantum mechanics in imaginary time is less simple than what you have, what you might think. Okay, but nevertheless, you can prove a remarkable identity actually, that basically we can somehow treat the problem in imaginary time as we did in real time at the price of modifying the dispersion relation. Okay, so basically this correlation function will be still a double integral, but now instead of having just y epsilon k, which will be the usual term that you get, you have to add a term in the dispersion which is r, so it's related to r, times epsilon tilde, and epsilon tilde is a remarkable object. It's the Hilbert transform of the dispersion relation. Okay, so that's the key technical ingredient that you have to work out to compute correlation function in imaginary time. So basically this Hilbert transform, what it does is a black box that you input a cosine and it gives you a sine. So you expand all your function in Fourier transform and then you get the Hilbert transform just by this observation. Right. Okay, so this is the main ingredient. Now let me also do another observation. The observation is the following. So all the correlation functions in the asymptotic regime, they can be determined by stationary phase analysis. Okay, so the stationary points, I call it z now. So z is a function of x, y, and it is the stationary points. Right, so you have to take this modified dispersion, take the derivative, and find the solution of the equation that you get. Okay, so now let me take this two-point function when the points x and y and x prime, y prime, they are close to each other. Okay, so the limit in which z is going to z prime. So from the explicit stationary phase approximation, you get this function. So there are some phases which comes from expanding the phase of the stationary phase. There is a real part which is nothing but the second derivative of this modified dispersion relation evaluated at the stationary points, which I write this way, exponential sigma plus sigma prime over 2, and is related to the curvature of the dispersion, so the second derivative of the dispersion. And then you have this denominator here. So now we would like to ask the following question, as I mean normally you would like to ask. So we have a large distance correlation, and we want to ask the question whether we can extract this correlation function, of course a posteriori, from a certain field theory. That's what you usually do when you consider lattice models, right? You compute correlation function, then you look at what happens at large distances, and then you try to infer a field theory. Okay, so that's so we have to build a field theory such that the correlation function of a free fermionic field, because here I mean there are only free fermions, is given by this expression here, which is I get rid of this 2 pi I by absorbing into the definition of the field phi. So if it was not for the phases, then of course we know what will be this field theory, because if the phases are not there, then this is the usual propagator, well, in this coordinate system of a free Dirac action. But since you have these phases, and actually this phase is this phase here, you can never get rid. This you might absorb in the definition of psi, because you have U1 symmetry, but not this one. So the field theory that you have to write is this one now. You can prove actually that if you take this field theory here and you compute the Green function, you get this one. Okay, but this field theory is the field theory of a free Dirac fermion, but in a curved background, right? And this curved background has to do directly with the fact that the dispersion relation is curved. There is a curvature in the dispersion relation. Okay, this is a posteriori, because if you don't know, of course, the stationary phase solution, you can never come up with this action. But still, it's an interesting point, I think. So basically, the fact that you have a curvature in the dispersion relation, that you feel this curvature inside because of the stationary phase, gives you a metric in the field theory. Okay. So, right, now, as I promised, let me explain you this how you actually get the real Arctic circle. So there are some steps to do. There are actually 3 steps from passing to this free fermion model, which was which had continuous time, to the dimer model. So there are 3 steps. So the first step is that I have to tell you where are the fermions on this dimer model, right? And the fermions, they live on the edges. So suppose I'm taking a square lattice like here, and I draw a reference configuration for the dimers like this one. Then I superimpose a random configuration for the dimers, and I put them together, killing the dimers which belongs at the same time to the reference and to the random configuration. So what I get is this. So I get non-intersecting paths on the lattice. And you might think to these paths as fermions, because they never intersect. It's a choice, but it's a self-consistent choice. Okay, so basically I'm saying that I will have a fermion on the vertical edge every time that I have a dimer which belongs to the reference configuration or to the random configuration, but not to both. Okay? And then I can upgrade the configuration according to simple rules for the fermions now. So I need for doing that I need 2 species of fermions, because I have to respect the dimer rule. So I need fermions on the even edges, which I call A, and fermions on the odd edges, which I call B. And I need a transfer matrix which implements this, basically this elementary moves that the fermion can do. They can just hop to the right or to the left, or stay, let's say, or going straight ahead, like this. Okay, so then what is the Hamiltonian? Well, the Hamiltonian is the logarithm of this product of transfer matrix. So now I have a free fermion problem, respectable, with a new Hamiltonian, which is the logarithm of the product of these 2 transfer matrices. Right? So the third ingredient that I have to tell you is where is the Aztec diamond, because I'm starting from a square lattice now. So the Aztec diamond is actually easy to build, because you can impose this boundary condition for the dimer on the square lattice. So I put dimer here, no dimer here, dimer here, no dimer here, But here you see that I leave one edge empty. So I introduce this staggering in a way here. So now think to superimpose your reference configuration to this boundary condition, and you see that here you fill all the fermions, and here you have no fermions. If you think that's what happens. And if I impose this boundary condition, then I froze the orientation of the dimers here, and I build really an Aztec diamond. So all in all, if I want to compute the density profile for dimers inside the real Arctic circle, the one of dimers, not the one of the fermions in continuous time, then what I have to do is I have to start with my initial domain wall state in which I fill up the fermions. There is a fermion here, so all the fermions they are on the left, and no fermions on the right. I have to evolve with an Hamiltonian which is more nasty than the simple open one, but is a perfect, respectable, let's say, free fermion Hamiltonian, which is the logarithm of the transfer matrix, measure the density, and then evolve again with in imaginary time. And so this is the result that we got by doing the stationary phase analysis. So this is the picture of the density profile for dimers on the square lattice using this technique of let's say using this free fermionic idea. So this is the density, and this is actually the same result, the famous result of Shor, Prop, and Jokush, I don't remember. So it's this result. And you see that there is a difference between there is an interesting difference between the circle for dimers and the circle for the fermions, for the simple because the difference is that it doesn't touch the boundary here. And this has to do with discrete time evolution. Because when you take discrete time evolution, you always build a light cone. So basically, if you want, you have to. If you take the Hamiltonian limit of this lattice here, you go back to the fermion problem and you squeeze this light cone on the boundary. That's the.
Because I mean, the radius of the circle introduces another length scale relative to what?
No, the radius of this circle.
No, the picture.
Yeah. Yeah, in this case, this is r over 2, the radius of the circle, but there is only or r over square root of 2, probably.
The question is, if you make it...
but this depends on the parameters that you put on the lattice. So I choose the parameter to get a circle, but if you change the parameters, so for example, if you give to the dimers a fugacity, you say the dimers on the left that they go through the, then you have an ellipse, you have and you can also, that's the way in which you actually get the Hamiltonian limit. You have to, okay. So now I finished. So these are the conclusions. So I spoke about inhomogeneous quenches in real time. There are many interesting questions, like for example, if you can write some quench action approach, if you can if you can actually understand this better, this universality that arises when it doesn't work, when it works. Then another interesting point is that you always have, especially when you have this quench from domain wall initial state that is really excited, so the initial state is really excited, then the curvature of the dispersion matters. You can never forget, because this introduces a background, and the field theory that will describe large distance correlation, it will have a non-trivial metric which depends on actually the fact that the dispersion is curved. And then the other point is that imaginary time is actually real, because well, we get the Arctic circle phenomena by doing quenches in imaginary time. Right. So thanks for your attention.
questions? Suggestions? I mean, once you have this method, you can study other combinatorial situations.
Yes.
Right?
Yes.
What kind of things?
But for example, a slight variation that you can do are dimers on the hexagonal lattice, for example, and the 6-vertex model also. It's slightly different, but you can also do. Well, maybe some other. You can also think to have, let's say, initial state which are not really like this domain wall initial state, but because they produce some let's say, so for example, you can displace the initial, so you have a domain wall here, then you move a bit the domain wall, and then you get some other limiting shape that were studied by mathematicians. But the problem of this technology, it is that it relies on the fact that you have a free theory behind. That's the limitation.
I'd just like to make another comment on your beautiful talk, but a general comment and historical comment on the use of the word Loschmidt echo to describe the return amplitude. Loschmidt was a contemporary of Boltzmann, and he pointed out that if you evolve with a Hamiltonian for time t and then with minus the Hamiltonian for time t, you get back to the initial state. And so this was an argument against Boltzmann's ideas about entropy and irreversibility. So that's the Loschmidt echo, more or less, when you evolve with a Hamiltonian h and then a slightly different Hamiltonian minus h prime.
Yeah.
And here you're setting h prime equal to 0, and it's a long way from h, so it's not the Loschmidt echo.
Yeah, that's correct. Actually, I use this terminology not.
I don't know when it started
Yeah.
to become termed the Loschmidt echo, but it's
Yeah.
not.
Also, Lea Santos, other people, they told me that is not exactly the.
Guilty party is probably somewhere around here. No? We have to find that out.
One question about the effective field cube that you get inside the frequency, the
Yes.
one with the curvature.
Yes.
So you said that you can derive it just from the scaling limit of the correlation function.
A posteriori, yes.
Do you think there is some RT argument so that even with adding something irrelevant, you can still get the same thing?
Yeah, there were some ideas, right? Also from I think people here that is somehow, let's say, non-trivial metric will emerge because of irrelevant perturbation that you had to the CFT. But I mean, I didn't.
Because it doesn't seem to be an effect of CFT, no? It's related to the curvature of.
Yeah, in this case, it's because you are so excited, the particle number is conserved, and basically you never see the flat part of the spectrum. You have always a curvature in the spectrum that you have to take into account, and it's precisely what actually gives the metric at the end.
There was another question.
Yeah, I was just going to ask if there's any results of interest in the corrections to the fluctuations of the Arctic Circle. So the fluctuations.
Yeah. So right. So for the fluctuation, you somehow near the boundary of the circle. So it's quite clear from this picture that you get still the Tracy-Widom distribution. It's immediate actually, because it's the same problem that for the real time you translate in imaginary time, and you see immediately that you have Tracy-Widom distribution for the fluctuation at the boundary of the Arctic Circle. Exactly the same. Yeah, so in this sense it's simple. There is a simple answer.
Okay, well, let's take the speaker again.